Welcome back, everyone. Today we're going to be starting at Chapter 2, which is the last chapter in Unit 1. In Chapter 2, we're going to go through an introduction to the elements. We're going to start learning about the atomic theory and the structure of the atom and the different subatomic particles and how they work. As we've learned, elements are the fundamental building blocks of more complex forms of matter. Specifically, elements are substances that cannot be decomposed into simpler substances. Every element is described using a name and a symbol. For example, gold is also described as the symbol Au. These symbols are unique for every element so that we don't have any ambiguity about which element we're discussing. Let's go take a look at some of those symbols and see what they mean. When we're first learning about the symbols of elements, it's very important to pay attention to one particular rule about these symbols. Some elements have a single letter for their symbol. Here are some examples. Hydrogen has the symbol H, carbon has the symbol C, oxygen has the symbol O, and sulfur has the symbol S. These symbols are always a capitalized version of the letter. Other elements use two letters as a part of their symbols. So for example, helium has the symbol He, aluminum is Al, chlorine is Cl, and silicon is Si. Notice that the second letter in these examples is always a lowercase. If we made those a capital letter, we'd be confusing those symbols with another element. So for example, if we wrote down SI when we meant silicon, we'd actually be writing down sulfur and iodine's symbols. This would be incorrect. Now, one of the fun things we're going to do in this class is learn the names for the various symbols. Knowing the names for the symbols gives us a lot of power to describe various chemical reactions and communicate all of that information. You might be surprised you already know several of these names. For example, you probably already know that the symbol O represents the element oxygen. What about some of the other symbols? Do you know what Cu stands for? That's right, Cu stands for copper. You might be wondering why we don't say Co for copper since it's spelled Copper. Well, that's because we've known about copper for a very long time. In fact, back in ancient Rome, they called copper cuprum. Take a moment and pause the video and see if you can write down the names, even if it's just a guess, for the symbols that I've shown here. You might be surprised that you know more than you think. Now, if you don't know any of them, that's fine too. We're going to start learning more and more about these as we go through the class. So hopefully you've had a chance to write down some of the names for these symbols. Let's start here with Mn. Mn stands for the element manganese. Don't get manganese confused with magnesium, which has the symbol Mg. Manganese is an element known as a transition metal, and it has very interesting properties in certain situations that give it very interesting colors. Now, that's not to say magnesium isn't also very interesting. It is. It's a shiny silver metal that burns very brightly with a white flame. You'll actually be burning magnesium yourself in lab in a few weeks. The symbol N stands for nitrogen, and the capital symbol I stands for iodine. Iodine and its purple crystals are probably one of my favorite elements. It's in a group of elements known as the halogens. You're going to learn the other halogens soon. Those are fluorine, chlorine, bromine, and iodine. Notice that I say iodine rather than iodine. It's a subtle difference in pronunciation, but you can show that you're in the chemistry know-how by referring to all of the halogens like this. So instead of saying iodine, I say iodine. Just like I say chlorine instead of chlorine. What if we have N capital I? Well, that's right, that's not an element because the second letter there is capitalized. This would stand for a compound containing nitrogen and iodine. If what we meant to write was nickel, we would have to use the symbol Ni. So if you got those right, great job. Now, a really popular question to ask at this stage is, do I need to memorize the elements? And my reply would be, why wouldn't you want to? Actually, it's really useful to know the names of the elements on the periodic table. Now, as you go forward in the class, it's definitely going to be an essential thing to be able to name things when you see the symbols, or provide symbols for the names. Now, when you look at the periodic table, you'll see there's a lot of information, and we haven't covered really any of it yet. We're going to be going through the periodic table in detail in the next unit. What would you want to take from this periodic table, and what would you want to memorize? Well, you don't need to memorize the positions of individual elements or really any of the numbers. What you would want to know, however, are the names and which names belong to which symbols. So I'll leave it at that. Go ahead and learn the names for the symbols and the symbols for the names, and I would probably start somewhere like at the top of the periodic table and gradually move down. You might notice that the periodic table that we have on Canvas, which you should print out because we're going to be using it for the rest of the course, omits the names for the different elemental symbols. You can use this periodic table, therefore, as a study tool to help you figure out which elements you still need to learn the names for. So we're going to save a detailed discussion of the periodic table for another lesson. Right now, what we want to do is talk about how are these elements made? What is their composition? To understand matter, we need to understand what makes one element unique from another, since all matter is made up of these elements. To do this, we're going to discuss the atomic theory. The atomic theory is the widely accepted theory that all matter is composed of tiny, indivisible particles that we call atoms. This atomic theory was first proposed in early Greek civilization by philosophers like Democritus. In modern times, we thank John Dalton for what we consider the pioneer of the atomic theory that we use now. Let's go to the next page and learn what John Dalton proposed as this atomic theory and see how it lines up with our current understanding of the atom. John Dalton's atomic theory put forward 4 key conclusions. Let's go through each of these and discuss. In the first part of John Dalton's atomic theory, he proposed that all matter is made up of very small, indivisible particles that we call atoms. This word atom John Dalton took from the original Greek, and in Greek the word atom means uncuttable or indivisible. Philosophically, this idea comes from the fact that we probably live in a finite universe and that at some point matter won't be able to be divided anymore. Therefore, at some stage it must end, and we call that smallest particle an atom. Now, this isn't the only conclusion that John Dalton put forward. He also put forward that atoms of the same type must be identical and have the same properties as a result. If these atoms were not identical, it's unlikely that we would see compounds that have the same properties. If they have the same properties, then the things making them up should also have the same properties. So this makes sense. We can think of this idea as making atoms kind of like building blocks that we can make more complex forms of matter from. And that brings us to John Dalton's third idea. In John Dalton's third point, he said that atoms combine together in simple, whole number ratios to form compounds. These compounds are the more complex forms of matter that I just mentioned. These compounds are formed from the combinations of atoms that comprise them. Now, let's just finish writing this one out and then talk about another point that I want to mention. What does he mean by simple whole number ratios for atoms combining? Well, what he means is that if atoms are indivisible, they would have to combine in whole number ratios. We can have one atom or two atoms combining with another one or two atoms, but we can't have fractional atoms. That's because he defined atoms as being indivisible. Now you might ask the question, how do they actually do this combining in different ratios to form compounds? Well, that's what we call chemical reactions. Dalton proposed that chemical reactions are these very rearrangements of atoms into different combinations and ratios. This is where we get all of the unique various compounds that we have by taking the building blocks and putting them together in different ways. One of the really nice things about this class is we're going to have the chance to actually learn all of the different ways that atoms combine in chemical reactions. Now, it turns out, while John Dalton gave us a really good starting point for trying to understand how matter works and why it does what it does, some of these conclusions we now know to be false. Now, the reason for this discrepancy is that in John Dalton's time, the atom was a brand new concept, and there were really no experiments for him to base his theory on. Now, that's not the case now. There are many experiments we have to draw on, and we have altered John Dalton's atomic theory to make a new, more modern theory. Let's start learning about some of those experiments now. Let's talk first about the discovery of the electron. The electron is what's known as a subatomic particle. That means it's a particle that's actually smaller than the atom and is a part of the atom. Now, John Dalton said that the atom was indivisible, and the discovery of the electron, therefore, invalidated that conclusion. Now, what are these electrons like? Well, it turns out they're very, very, very small. They're 1/1000th the size of an atom. Their mass is very insignificant. In fact, when we add up the entire mass of the atom, we don't usually even include the mass of the electrons. Now, a very important property of electrons is the fact that they are charged. They have what we call a negative charge. A negative charge is just an electrical charge that happens to be the opposite of the other charge that we call positive. Positive and negative charges are obviously opposite to one another, and electrons have a -1 charge. So each electron particle is -1. So if we have 2 electrons, it would be -2 in total, because each one has a -1 charge. Now here's a note. Electrons from one element are identical in properties to electrons found in another element. There are no differences between these different electrons from different places. They're all the same. Now, how was the electron actually discovered? Well, J.J. Thomson discovered the electron way back in the early 1900s. He used something called a cathode ray tube, otherwise known as a CRT tube. In this experiment, an electron is produced from the excitation of an atom within a vacuum tube. J.J. Thomson observed a beam that glows in a very interesting and beautiful color that he was able to deflect with magnetic plates. J.J. Thomson was able to assign the electrical charge of this beam of subatomic particles by noting the direction in which it deflected. Notice it's deflecting here in this diagram towards the positive plate and away from the negative plate. We know that positive and negative charges attract one another, so that's why we were able to assign the negative charge to this. It took many other scientists and many different experiments to actually determine the mass and the size of the electron, as well as the magnitude of its charge. But we credit J.J. Thomson with actually discovering this first subatomic particle. Let's go on to the next page where we'll learn about other subatomic particles that were discovered soon after J.J. Thomson's original discovery. Let's talk about the discovery of the nucleus. After the discovery of the electron, logic held that there must be other subatomic particles in the atom. Why is that? Well, consider this. If we know that atoms as a whole are neutral, and then an electron can be taken away from one, that would mean that what's left behind must be positive. And where does that positive charge come from? Well, scientists presumed that there must be a positively charged particle to balance out the negatively charged electron. We now describe these positively charged subatomic particles as protons. Protons were first observed in an experiment that is now known as Rutherford's famous gold foil experiment. In this experiment, a stream of alpha particles, which are positively charged particles moving at a very high velocity, were beamed at a very thin foil made from gold. Gold foil was chosen for this experiment because of the unique properties of gold. It turns out that gold can be pressed out into very, very fine sheets. It was these very fine sheets of gold that were only several atoms thick that Rutherford used in this experiment. Because it was known that positive charge must exist inside of these gold atoms, it would be expected that most of the beams would actually bounce backwards when they collided with the gold foil. That makes sense if we imagine the fact that a positively charged particle will repel strongly another positively charged particle. So the alpha particles, which are positive, should collide with a positive gold nucleus and then bounce back. The very surprising thing about this experiment is that only a few of those beams actually bounced back. Most of them, 99% or greater of them, went straight through. The conclusion of this is quite striking. A very good analogy would be throwing a baseball at a wall and then it appearing on the other side. Now, what does this experimental result say about the structure of the atom? What it says is that the volume of an atom is mostly empty space. It also says that the positive charge of the atom is very small, and it must be very far away from the negative part of the atom, the electron. So if we have an electron outside of this positive charge center, most of the space in between is simply empty. How do we know that the positive charge is very small? Well, that's because we do get some ricochet back. If 1 or 2% of the alpha particles bounce back, that means 1 or 2% of those particles collided with something that's positively charged. That means the probability of them hitting a positive charge is very small, because that positive charge must be in a very small space. Rutherford is famous for saying that after this experiment, he woke up the next morning and was worried he might fall through the floor because of all of the empty space around the atom. Let's take a moment and summarize what we just discussed. The Rutherford gold foil experiment demonstrated the presence of a very small, positively charged region that we call the nucleus. Most of the atom outside of the nucleus is empty space until we reach the electron, which has an opposite charge. So we have the nucleus of an atom, and we also have something now that we call a nucleon. A nucleon is a particle that exists within the nucleus region of the atom. It's a citizen of the nucleus. Now, it turns out we've just discussed the proton, which is one of the nucleons. It's the positively charged nucleon. It has a mass of 1, that's called an atomic mass unit, or AMU. Now, there is also another type of nucleon, another citizen of the nucleus. These are called neutrons. Neutrons, like protons, also have a mass unit of 1, so they're the same mass. However, their charges are not the same. Nucleons do not have a charge. They're neutral. What do neutrons actually do? Why are they there? Well, we're going to learn about that a lot later in the course, but for now, note that nucleons help hold together the nucleus of the atom. They're essentially nuclear glue. Without them, the atom nucleus would just fly apart. It's from these 3 basic building blocks that atoms are constructed. We have electrons, protons, and neutrons. Now, it turns out atoms have different amounts of these different subatomic particles, and that has a direct effect on the properties of an atom. The properties of an atom are determined by the amount of each of these subatomic particles. Let's take a look at that here in part 3. In part 3, we're going to be discussing something known as the atomic number, the mass number, and isotopes. First, let's talk about atomic number. Each type of atom that we have has a unique number of protons in its nucleus. Now, the number of protons in the nucleus turns out to identify the type of atom that we're discussing. We call this number, the number of protons, the atomic number. Now, when 2 atoms have a different atomic number, that is, a different number of protons, they are different atoms. When 2 atoms have the same number of protons, they are of the same type of atom. Now, how do you know an element's atomic number? Actually, it's shown on the periodic table. I've shown an example of that here. The atomic number is the whole number, because there's a whole number of protons, shown near the element. So for example, carbon has an atomic number of 6. That means a carbon atom will have 6 protons. Now, if there's another atom, and it has 6 protons, it's also a type of carbon atom. However, if we have something that has 7 protons, it's not carbon. Let's go to the next page and take a look at some examples of that. In this table, I have various element names and a place for their symbol and atomic number. Some of this information is missing. Let's see if we can figure out what the missing spaces are. Let me show you the first example, and then you'll have a chance to pause the video and try a few yourself. So first, we see the element name hydrogen. What's the symbol for hydrogen? That's correct. The symbol for hydrogen is the letter H. Now, what about hydrogen's atomic number? Hydrogen has an atomic number of 1. How do I know that hydrogen's atomic number is 1? Well, I looked at the periodic table and found the symbol H and noticed that it has the atomic number 1 listed there. So how many protons are there in the nucleus of a hydrogen atom? That's correct, there is 1. All right, let's check out lithium. What's the symbol for lithium? If you don't know, it's Li. And we see that lithium has an atomic number of 3, so there are 3 protons in lithium's nucleus. Now we get to the third row. We see the atomic number is here, but not the symbol or the element's name. Go take a look at the periodic table and see if you can find and identify this element. Now, if you found that element 26 has the symbol Fe, that's correct. Fe is the symbol that we use for the element iron. Why does it have Fe and not something like In? Well, that's because the Latin word for iron is ferrous or ferrum. So if you've gotten that one right, great job. Let's take a look at the next row. Here we see the atomic number 47. Go look up 47 on the periodic table and you'll find that it has the symbol Ag. Do you happen to know what Ag stands for? That's correct, it stands for silver. That also comes from the Latin word that we use to describe this metal. The Latin word is argentum. Gold has the symbol Au, and the Latin word for gold is aurum. So, how many protons are there in the nucleus of a silver atom? That's correct. There are 47 protons in silver. Having that many protons gives silver some very interesting properties. And now we get to lead. Let's figure out what lead's atomic number is, and then we'll figure out what its symbol is. Lead has the atomic number of 82, and its symbol is unusually Pb. Why does lead have the symbol Pb? Well, it turns out that stands for another Latin word. That word is plumbum. And you can imagine why the Romans might have called it this. They used lead to form many of their aqueducts, which transported water from one place to another in ancient Rome. Now that we've gone through the basic structure of atoms and we've learned how one atom is different from another by its atomic number, that is the number of protons in its nucleus, we're going to stop this video here for now. This is the first video in a two-part video series for Chapter 2. In the next video, we're going to start looking at something called ions. These are charged atoms. They're charged because they have a different number of electrons than protons. After that, we'll also learn about the mass of atoms and something called isotopes. So with that, I'm going to end this particular video, and I will see you in the next one. Take care and let me know if you have any questions.